What? Okay, as a brief review. Negative is inward, positive is outward. Perfect. You took the question right out of me. Oh, hang on. I am so disorganized. It's 1 over R squared. Yeah. Too much graphing. Too much graphing? What? We don't do enough graphing. That's actual feedback that I've gotten back. I would not even say that. I would say we did. Okay. Okay. Which way does it go on a point charge? A positive point charge. Outwards. Well, we won't be writing in green. Okay. So where is the electric field the strongest? What? Where would the electric field be strongest around this point charge? Close. Okay, so electric field strength is strongest right in close to the point charge. Where would the electric field strength be weakest? Think about the formula. E is equal to KQ over R squared. Where would it be the weakest? The higher R gets, what happens to E? As R gets bigger and we then square it, it gets exponentially smaller. Okay? So it depends on the distance. And my phone is listening to me again. I don't know how to turn it off. I don't know how to tell my phone not to listen to me. Okay, well, if I have plates, and I make one plate positive and I make one plate negative, which way, and in order to do that, I have to connect a battery. When I look at this piece here, this is a symbol of a battery. Or a source of electricity. And you will always see a long line and a short line. A long line is positive and a short line is negative. Okay? A long line is positive, a short line is negative. And this typically is a battery, but it's a source of power is the technical term for it. Now, electric field strengths flow how from positive? Away, and they flow how with a negative? Towards. And we get a little bit of bowing out on this side, and a little bit of bowing out on this side. Okay? The thing with plates though, is the plates are fixed. There is a specific distance. I have to switch to a pen because this felt this. Oh, CJ, I just knocked your headphones off the ground. Sorry. I don't think they're broken. I'm sorry. Okay, this is a uniform electric field because the plate distance is fixed. Okay? Because the plate distance is fixed, we never use electric field strength is equal to KQ over R squared. Okay? So as soon as we're talking uniform plates, that formula goes out the window. So we never use E is equal to KQ over R squared. This one here over, however, we do use KQ over R squared because the distance is variable. Okay? So parallel plates is where we see uniform strength, and so we're going to need a different formula to figure out how to calculate that electric field strength, but we have to understand how potential energy works. Well, here's the great part. We flog potential energy pretty hard in Science 8 and in Physics 20. And so we have potential energy we know is highest here before we are in motion and lowest here once we are in motion. So this is low EP and this is high EP. What is the energy? Because we always focus on the law of conservation of energy, what is the opposing energy? If you're not stationary, you're moving. So what energy represents movement? Kinetic energy. We're going to have a low EK here, and we're going to have a high EK here. Okay? That's when we're looking at gravitational potential energy. Well, we have the same language with electric potential energy. When I look at this diagram, which way is my battery? Negatives at the top, positives at the bottom, which means that this plate is a negative plate and this plate is a positive plate. So I could have unidentified plates, and as long as I remember how to read a battery symbol diagram, I know which plate is which. Now, which way is the electric field strength going in this scenario? Towards the negative. Okay, so we have electric field strength going this way. If I have a negatively charged particle here which way is that negatively charged particle going to go? Towards the positive. It's going to be repelled from the negative plate. So here it has an incredibly high potential energy and a low EK. As it moves towards, right, because only the electrons move, as it moves towards the positive plate, it now has low EP, because that's where it wants to be, and high EK. And we see that potential energy is being converted into kinetic energy. So what could we say in terms of repulsion and attraction? What kind of energy does repulsion have? Let me change the question around, make it a little bit easier for you. What amount of potential energy does repulsion have? High or low? High. It has high potential energy. Right? Because that negative charge does not want to sit up against that negative plate. If I have attraction, what kind of potential energy do I have? What kind of potential energy do I have? High or low? Low. Right? It's going to be in motion. Like Daniel said, it's going to have high kinetic energy. It's going to be in motion. The negative is going to move towards the positive. Right here, converted into. Okay? So, here's the big key part. Uniform electric fields are a method to accelerate or decelerate charged particles. I don't know what happened to my pink highlighter. Okay? All right. So we can find out the potential difference. So the potential, it's called several different things, and it is interchangeable. So the electric potential difference is also code word for electric potential, is also code word for voltage. Okay? And when we look at the change in voltage, we see that there's a relationship between the change in energy and the charge. Now we're dealing with two E's. This E is electric field strength. This E is energy. Energy is measured in what unit? Joules. Electric field strength is measured in a Newton per Coulomb. Okay? Base unit is joule. Base unit is Coulomb. If you have a kilojoule, megajoule, a microcoulomb, you need to convert it. The great thing about potential difference is that it's scalar. We do not need a direction. small amounts of energy, so when we're talking times 10 to the negative 8 times 10 to the negative 6 joules, we can convert that into electron volts, and it's a relationship in regards to electrons. So joules are SI units, and so we need to make sure that everything is done in a joule. 1 electron volt, which is what EV stands for, is related to 1.6 times 10 to the negative 19 joules. Kyle? Yep. Okay, so let's just practice this. Let's convert 2.10 electron volts into joules. When we look at our want over our have, we have electron volts. So 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. We have joules on top. That's what we want. So 2.10 times 1.6 times 10 to the negative 19 gives me what for a value? (3.36 times 10 to the negative 19). Okay. Now, since the electric potential energy is changing in a set of parallel plates based on how much repulsion there is, how much attraction there is, electric potential is changing even though the electric field remains constant. So what does that look like? Here's one parallel plate. Here's another parallel plate. Pay attention to the battery. Which is my positive plate? My top one, because this is the positive end of the battery. Okay, so there's 100 volts going through this power source. Which way is my electric field strength going? Which way? Towards the negative. Okay, this is my electric field strength. But what we find is here we have 0 volts. In this region, somewhat close to the negative plate, we're going to have 25 volts. Halfway, we'll have 50 volts. 3/4 of the way, we'll have 75 volts. And right up here, we'll have 100 volts. Because the positive charge will want to move towards the negative plate. So we'll have increasing, it'll have a phenomenal amount of potential energy here and all kinetic energy here. Okay? It doesn't matter where that particle is inside of those two plates, the electric field strength is the same everywhere. But the potential difference changes because the potential energy is different throughout. Are we following that concept? Thumbs up, thumbs sideways, thumbs down, thumbs sideways. That's okay. I can do that. Nope, the electric field strength is throughout the whole thing between the plates. Okay? And the reason it's uniform is because the distance between these two plates is fixed. So if I look at E equals KQ over R squared, if I always have the same distance, no matter where I'm at in my formula, my electric field strength will never change. But if I put a positively charged ion here, what does it want to do? It wants to go towards the negative. The positive plate will repel it and it will move. So this is very high potential energy, and when it gets here, is very low potential energy. If I looked at it, I don't know if my thing will work. Here, what does this negatively charged particle want to do? It wants to go this way. Ah, the pen doesn't work. It wants to go this way. And so then my potential would be different. If I had a negatively charged particle come into this, then I would see that this would be my 100 volts, this would be my 75, this would be my 50, this would be my 25, and this would be my 0. Stop listening to me. Because this is very high EP, and when it gets here, this is very low EP for a negatively charged particle. The red lines go down because the electric field strength always flows away from the positive plate and always in towards a negative. Always, never changes. Okay? All right. It's a good question. Okay, let's look at the second question. Okay, an electron has a speed of 5.8 times 10 to the 5 meters per second when it enters a set of parallel plates. If the electric potential difference between the plates is 140 volts, what is the exit speed of the electron? Let's first decode some of this. What's the information that we have in here? Okay. What's that, Kyle? Okay. What's some more pieces of information? Velocity. Okay. And what is the question asking us to find? The exit speed. How would we identify between those two? VI and VF. Okay. When we're talking velocity and we know that we're sitting here between a set of parallel plates, we're going to find velocity using 1/2 mv squared. Okay. Now, do we have the mass? Yes. And it's what? Yes, it is electron. Okay. And so we're looking for VF. How do we find? That means that we're looking for EKF. How do we find EKF? How would we find a final something? Will we find it from a change in? Now, can we figure out EKI? 1/2 MVI squared. If you look on your data side of your table, if you look up for mass of an electron, 9 point, yeah, because in the question it says an electron. You would have to be told. It could say a proton, it could say an alpha particle. Can we find change in energy? Pretty sure we just learned a formula that gives us change in energy. Yep, delta V times Q. What's my Q? It's a Q of an electron, which is? Yep, you're correct. Oh, that happens to be the same number, actually. But one's in joules and one's in coulombs. Okay, so let's work backwards. Delta E is equal to? What unit? Energy. Joules. That would be why. Okay, now that I have delta E, I can find delta EK, or I can find EKF. Oh, this is squared. Don't forget to square your velocity. All right, 2.2255 times 10 to the negative 17. Now I can solve for my final velocity because I have EKF is equal to 1/2 mv squared. So when I rearrange formula, I'm going to get 2EK divided by m, all square rooted, is going to be equal to my VF. So when I plug in my numbers, I get what? Okay, so 7.0365 carrying on times 10 to the 6 meters per second. But the question says what for significant digits? 3. 7.04 times 10 to the 6 meters per second. And when I go back to the question, it says, what is the speed of an electron. So do I need direction? No. Speed is scalar. So 7.04 times 10 to the 6 meters per second. All right. I should put the answer here. And then turn the recording on. That makes sense. Yep. All right. The diagram below shows two parallel plates separated by 10 centimeters. Calculate the change in voltage between points 1 and point 2 when they are 4 centimeters apart. So this means that this whole plate here, top to bottom, is 10 centimeters, and these two here are 4 centimeters apart. This is the positive end of my battery. This is the negative end of my battery. So when I see uniform plates, I know that I have uniform electric field strength, but that I have changing voltage. Remember, as I go through the different depths of the plates, my voltage changes. So I'm going to have between the plates, and I'm going to have within the plates. Now, between the plates, this is where I'm going to put my information. Between the plates, my delta V is 1.2 times 10 to the 3 volts. And my distance between those plates is what? Between the plates, 10 centimeters, otherwise known as 0.1 meter. Okay? Now within my plates, it's asking us calculate the voltage within the plates when the two particles are 0.04 meters apart. So how do I find voltage? Oops. Electric field strength, sorry. Electric field strength between is equal to the change in voltage between the two particles divided by their distance. And how do I figure out this electric field strength? Because it's uniform, I can say that my electric field strength is going to be my initial voltage, or my between the plates voltage, and that distance. Oh, sorry. Okay. Yeah, or V1. If I call this V1, this is V2. VI, VF. They're not really VI, VF. They're V1, V2. So if I'm looking at my uniform electric field strength, I can go 1.2 times 10 to the 3 volts divided by 0.1 meter. And I'm going to get an electric field strength. Its units are newtons per coulomb. So now that I have electric field strength, which is uniform anywhere between those 2 points, I can take that value and I can solve for E2, or I can solve for potential difference too when I look at those distances. So the potential difference between two particles 4 centimeters apart inside a set of plates that are 10 centimeters apart is equal to what? 480 volts. Okay? All right, so we're going to work on these questions. In class, we're going to focus on the practice problems 1 through 6. And then tomorrow we'll finish off this lesson. Yeah, but we're going to focus on practice problems 1 through 6. But tonight, what we don't get done in class, you're going to push through and do these ones. The thing with Physics 30 is you have to practice. You have to see the multitude of ways that they can ask you a question. You cannot go through Physics 30 and only do the example problems that we do in class. It's not enough practice. It's not enough immersion in the math, okay?